So what's our analysis? What's the analysis? What do you got? Anything else?
Nothing in the fingerprint.
You got fingerprint. Crossing it out is generally a bad idea, but not a horrible thing. Because there's information there. I really hate it when people just cross it out, because there's information there. It's not hard?
No, it kind of is.
It can be. So what you can do is just get a piece of paper and just cover up anything 1500 or under. 30 seconds.
And then one, you don't know.
I guess I gotta pause the video. What do we got? 4 unique. It says unique carbons. What else do we have? 3 alkanes.
One everything else.
And 1, who the hell knows? Minute? What do I expect you to get out of this? What do we have? We have a 110 for our molecular weight. No +2. No nitrogen because, well, actually we'll not worry about the because yet. No +2, no nitrogen, bromine, chlorine, or iodine. Okay. Anybody else take it to the next step? Molecular formula would be the next step. Did anybody jump that far?
C6H12.
Wow. C8H14 is a possibility. Yes. Damn. Sorry. I won't answer that. Where are we? Minute?
3 unique signals.
3 unique. I want a little bit more than signals. Hydrogens. Okay. Anybody get anything else?
Multiplicity of 3.
I heard alkanes.
2 alkanes, 1 everything else.
Okay, now I'm hearing a giant cacophony of other pieces. Okay. So, shall we go back through these so you can take a minute, take a picture if you want, because I will be asking them again. You guys want that? Okay. So we'll go back to the beginning. And as we go back through these while you're taking pictures, I'll ask the other question. The question was made about, so feel free to take pictures if you want them. A question was made about how do we know what we're looking at? How do we know that was carbon NMR or H NMR? You should be able to look at these very quickly and say which spectra it is. Okay, so for this one, we know we're looking at IR because okay, we can see a lot of peaks. I would say percent transmittance and wave numbers. Look at your axis labels. That's where I would jump to. So IR is the only one that does that. Hopefully we're done taking pictures. Unfortunately not. I'm not sure I'll have enough time. This one is carbon NMR, not our mass spec. Why is this one carbon NMR and not H NMR? So the ppm is what tells us that we're looking at NMR and not mass spec. Okay? And then the values of our ppms, we're going up to about 200, which is putting us at carbon NMR. And then, oh, good point. In our HNMR and our carbon NMR, notice our 0 to our number reads right to left, whereas when we look at our mass spec, it goes left to right. So we can look at that left to right versus right to left thing to help us trigger on which form of the spectra. The other thing I would look at is this M to Z, which stands for mass to charge ratio. Not a super big deal, but that's what's going on there. And you might look that it says relative intensity, but sometimes they ignore that. or it's not provided. And then the last one, because it's the last one, we know that's HNMR, but what are we looking for? We again have our ppms, and we're looking at values less than 14. Okay. Tells us we're looking at HNMR. Okay. All four of these spectra do belong to one compound. A request was made to go ahead and go through spectra, and I decided to make it a slightly trickier one, or less tricky than I think I set up on the last, or that was in the PowerPoint originally. But it does have a little trick associated with it. Okay? So feel free to go ahead and analyze that ahead of time. We will go through in more detail as we move through the days. So hopefully, what is that, Wednesday, I'll reveal a bit more bits of pieces of information about it. And then next Monday, we'll kind of finalize the structure and get to the point of why it was tricky. That said, we can now move into the really kind of tricky aspect, or almost move into that. Before we get into it, the plan. The exam is next Wednesday, which comes up very, very, very fast, which is why the spectroscopy stuff was provided right after the final, or right after the exam. Okay? We have chapter 5 to get through, and then it's the kind of weird nuances, weird things within spectroscopy. The videos gave you kind of, believe it or not, just the basics without getting into too trickiness with spectroscopy. Okay? So what we'll do is look through chapter 5, then we'll go through and look at 15 and 16, kind of the trickier aspects that might be a little bit more challenging. At most, you're looking at 1 or 2 questions on the exam based off of those, off the tricky parts. Okay? And then I'm hoping we'll have finished that mostly this week, and then Monday will be kind of a review of spectroscopy and looking at the nomenclature rules. Okay? So I may skip over nomenclature rules from this section to kind of leave that for the end. Okay? Because I think that's easier to deal with. Kind of make sense? Okay. So, chirality. Really ties back to our structure process, which is why it was part of our model lab. We're looking at defining structures according to something known as chirality. Okay? All structures have a handedness associated with them. Okay? That handedness may be identical, or it may be different, like a right and a left hand. Okay? Because of that handedness, we then go through and create these definitions. You end up with chiral and achiral. Chiral would be referencing things that really have a handedness, a right and a left hand. Okay? The definition from that is saying that we have non-superimposable mirror images. So if I take my right hand and drew its mirror image, which would be my left hand, and then tried to superimpose them, I would see that they can't superimpose. And we briefly talked about this. That does not mean clap your hands together and be like, oh, they're totally superimposing. Okay? The top must overlay with the top. When you try to superimpose your hands, you're bringing them completely over. They don't superimpose. The top does not superimpose with the top. Okay? They maintain that mirror image quality all the way through. Okay? Which is a tricky concept to process, particularly when you think about your hands. Okay? Achiral means that when we look at the mirror image, it is superimposable on it. So a table, these tables would be superimposable on their mirror image. Drew out the mirror image, all we do is slide it over and it would superimpose within it. Okay? So what we want to do is be able to look at structures and decide, are they chiral or are they achiral, based off of those definitions. Okay? Why this becomes particularly chemically important came into the 1950s. Okay? I believe it was Pasteur. Probably screwing that up. It was originally discovered with the molecule tartaric acid, which was isolated from wine. You notice that sometimes, if you're old enough or refined enough to drink really expensive wine, you'll notice sometimes they get crystals in it. Those crystals are tartaric acid. Okay? And what a scientist, who I believe was Pasteur, did was able to look at those crystals and notice that some of the crystals reflected light differently than others. So he manually went through and tweezed crystals out into 2 separate piles and noticed that they did indeed have different properties. Okay? What was the different properties? It turns out that they were right and left hands of the same molecule. Right? In and of itself, it was like, oh, whoopee, who do we care? They don't really do anything other than reflect light differently. Right? Where it became super important is when we move into the 1950s and we're now creating drugs for humans to ingest to go through and cure illnesses. And one of those drugs happens to be thalidomide. Interesting feature with thalidomide is it cured morning sickness. Right? So if you're a woman, you got sick, when getting pregnant, take this drug, awesome, great, phenomenal, didn't have to deal with morning sickness ever again. 9 months later, or however many months the whole gestation process is from when you were sick, okay, and you give birth, they noticed a strikingly high mutation rate. Okay? And they ended up tracking it back to the drug and sort of back to the drug, and it came down to one particular aspect of it. That when we looked at this drug, this carbon right there had an interesting feature associated with it. Notice that squiggle. What that squiggle is saying is that there is the potential for that to be a wedge bond or a dash bond. Okay? So if I drew out those two structures and tried to superimpose them, what I would find is they're non-superimposable. But all the atom connectivity is the same. Okay? Turns out they're mirror images of each other. Okay? Well, we'd think, well, if they're mirror images, who cares? Right and left hand can still do the same thing, unless you're left-handed and try and use right-handed scissors. Okay? Same thing was happening. When this drug was then ingested, half of it was the active ingredient to go through and quench morning sickness. The other half of it got metabolized by the body and turned into a mutagen, which then caused the babies to be born with flippers instead of extremities. Okay? Morning sickness or flippers. And so they ended up pulling the drug shortly after they made that connection. Okay? So this is chirality. This is kind of the origin of where it came from. And believe it or not, we have tons of molecules that we're ingesting every day that have chiral centers in them. Most of our biology is chiral. Okay? You look at your amino acids. There's 20 common amino acids. Of those 20, 19 are chiral. Only one is achiral. Okay, so we have a huge amount of chirality associated with biological systems, and if we're going to make drugs and give those drugs to people, we'd better make sure that that chirality doesn't inflict other damage. Okay? So it now comes down to how can we recognize and identify this. Okay? So if we take a look at the two compounds in the upper right-hand corner, okay, most people would look at that and say we got 4 carbons, we got a wedged chlorine, those would be identical, right? Are they? No. Turns out they aren't at all. If we tried to overlay the carbon backbone as it is, does it overlay? Does it superimpose? No. So what do we have to do to get it to superimpose? Turn the structure over. And since I've got space, I'll have to do it with the right one. So we flip that over. Whoops. Flip that over. Now our carbon backbone would line up. We say, well, then we just draw on the chlorine. Well, doesn't that superimpose? Where's the chlorine in the original drawing? Coming at you. Right? What happens if I rotate that structure? It's now going away, which then means that is not wedged, that is dashed. Okay? So that same three-dimensional manipulation that you had to do for that previous unit, the tail end, you now have to do with these structures, and you have to worry about these stupid wedges and dashes. Okay? So it makes it a little bit more challenging. This is where manipulating the models and having that spatial awareness can help you out. Okay? If you don't have it, that becomes very tricky to manipulate. Okay? There are tricks to get around it, but for the most part, you just kind of have to follow through it. For those of you that think that's really difficult and have a hard time seeing it, it's really difficult for me too, and I've been doing it for a little bit longer than you. Okay? It's also my least favorite unit to teach, because I will go through and say, what's the relationship between these structures? And some smart person in the audience will, oh, it's this. And I'll be like, what? And I'll have to draw out the structure, do all the stupid manipulations, and be like, yeah, you were right. Screw you. Thank you. Okay? So it takes time to go through and process and manipulate. You just have to work through it. Sometimes you just have to deal with those limitations and draw it all out. Okay? So our flow chart, if we went through our old flow chart, we'd start with A and B. Do they have the same molecular formula? Yes. Are they superimposable? No. Right? Do they have the same atom connectivity? Yes. This would slide them into the stereoisomers aspect. One of the things that we had discussed was that if we're looking at structural isomers, we would give them different names. Right? In stereoisomers, they end up with the same name. So that can be a bit of a problem. Okay? My right and left hand, right out of the gate, they have, what was that, Henry? They have different names. Have we addressed how to name them differently? No. That's your nomenclature rules. That's what's showing up in nomenclature chapter 3, I think, is just addressing those rules. Those of you in the lab, or those of you that looked at the lab activity that I posted, okay, there's a section that goes through how to address your structure to assign the nomenclature aspects for this. Okay? Again, it's one of those things that there are shortcuts online. I've seen people go, oh, all you got to do is this, and then I go through and do it, and I get the answer wrong. Okay, that means to me that that method sucks. I'm not going to do it. So the only way I do it is painfully long. That's what I'll teach you, and that's what I'll show you. If you can come up with another method that works consistently for you, good for you, use it. Okay? Just don't come crying to me when it didn't work. Okay? Well, you can come crying to me. I might just laugh. Okay? So, stereoisomers are really hinging on finding asymmetry within the molecule. Okay? So if we can find where we've lost symmetry, that can help us identify that that's where we are. Okay? So if we take a look at an old example up top, what's the difference between those structures? Cis and trans. Okay? This is sometimes referred to as geometric isomers. Okay? They are a category of stereoisomers, and sometimes they get placed in kind of weird locations. Okay? But there is an asymmetry there, right? If I go through and split the molecule there, well, it's symmetric, right? But what happens if I split it on this axis? Then it's asymmetric. It doesn't reflect the same across. So by finding that axis of asymmetry, I can address that it's going to have some kind of nuance associated with it within that stereoisomer category. If we move to the bottom two examples. We have a symmetry element within that structure. Whoa. Do we have one within the other? No. Okay. So while they may have the same atom connectivity, they don't have the same symmetry, which then means we're getting dropped into that stereoisomer category. Kind of makes sense? So we're just trying to find those aspects. Okay. Characteristics. So number one, in our cis-trans, what do we see as a commonality in those? Double bonds. Okay. Double bonds are a key feature because double bonds can't rotate. So that's where we're getting that cis-trans aspect. What's happening when we move down to the other structures? Why can't I rotate this bond? Can't I rotate that? Yeah, I can rotate that bond. Where does it end up? The exact same spot. Okay. What happens? What would my drawing look like if I rotate about that bond? Okay, and for those of you questioning this, this was on your test, and a lot of people said, oh, you can rotate about that. Yes, you can rotate about that bond. What does it look like? It looks exactly the same. What bond are you referencing, or the one that is potentially tricky? This one, now what happens? Now it looks like it flips. Okay, so be careful about what bond you're rotating. If I rotate about that red one as I've got it labeled, it stays dashed. To rotate that to get that wedged, I would have to rotate any one of the bonds within the ring. And that's why it was suggesting, what's the issue with that? can't rotate that bond because it's in a ring. Okay, so the ring can kind of help us out because the ring is effectively a double bond. Right? It's just a double bond that went through more carbons. Okay? What do we see in those bottom two structures? So yes, we could label it as a ring, but if we went back to the original example that I had, were these the same? No. But they don't have a ring. So is it the feature of it being a ring that prevents this superimposability? Or is there something else? What is a commonality between those ring structures and the ones up top? So we can say the orientation of the bond with respect to the rest of the structure. Okay. But if I had gone through and done this, are these two structures now superimposable? Is a carbon different from a carbon? No. Which means when I flip those, you're right. The original CH3 may be dashed, but all I've got to do is do a rotation and I drop a different CH3 that I can't tell the difference between into the exact same location. When you're looking at this drawing, you may be saying, well, this CH3 is attached to a wedge, so that makes it chemically different from the other one, or distinguishable. No, remember, you're looking at a model. Because we've got the model, I'm going to start calling you it. Say it. Just make a mess everywhere. Which one do I have in my hands, top or bottom? Sorry, got to get it a little bit set up. Hopefully we all see that we have the top one, right? Okay, how do I make it look like the bottom one? Well, I can do that. Did that just do it? Actually, I think it needs to do it like that, right? Okay, so, and you say, well, but that's not superimposable, right? That CH3 is now dashed, not wedged. What do I need? I needed, there it is. What do we have now? The exact same structure. So by changing the atom from a chlorine to a carbon, I lose that setup. What's going on? End up with the exact same structure. Whereas if that was chlorine, now I can't do it. Right? Made that a chlorine and tried to make that the other structure. So we could flip it over, and now what happens? It's dashed. Well, I'll just kind of do some kind of manipulation to get it to be wedged. Well, now it's wedged. Is the rest of the carbon chain superimposable? No. Huh. What changed?
Different atoms.
This is insanely difficult to see. What is going through that structure right now? A line of symmetry. A line of symmetry shows up when we have the methyls. As soon as we make that a chlorine, what happens to that line of symmetry? It disappears. Okay? This is why I find lines of symmetry really difficult to find. So ideally, we'd come up with another definition. What is a common feature of our chlorine structure and those rings that are shown? And And those of you that have read chapter 5 should already be jumping all over this definition. Should I throw in a key word? How about a stereocenter? Or a chiral atom? We have in each of those structures at least one stereocenter. At least one chiral atom. Because we have that chiral atom, we've lost our symmetry, which then means when we look at the mirror image, it becomes non-superimposable, and we now have chiral molecules. Okay, or chiral relationships, I should really say. Okay, so what makes it chiral? We need 4 different things attached. So you typically see the nice little drawing of simple carbon. Right? We could go through and label each of the 4 bonds on it. In the top case, what happened? Do I have 4 different things? No, I have 2 3s. Okay? Which then means when I look at its mirror image, they would be superimposable. Got a habit of doing that. Okay? What happens if we have 4 different things? Now they become non-superimposable. Okay? So if we look at a carbon structure and we can find an atom that has, or a single atom that has 4 distinguishable groups attached to it, we now have a chiral center. If we have a chiral center, our molecule now becomes chiral. What if we have more than one chiral atom? Well, that just opens up a can of worms into a whole new set of other differentiations. Okay? So when we're looking for asymmetry, some people can see the planes of symmetry. Okay? In this case, we have a plane of symmetry running right through the line or our flat aspect. What we're looking at here is the drawing. Hydrogen, whoops, that's an eraser. Hydrogen, green, and red. The plane of symmetry is aligned where we're cleaving immediately halfway through. You might say, well, but then isn't the green on one side and the red on the other? Remember what our drawing is showing? It's twisting it off axis so that we can clearly see and label those positions. We have to remember that that twist off axis doesn't destroy the plane of symmetry. It's still there. It's just now on a weird axis off to the side. So we do have a plane of symmetry in that molecule. What happens if we add on a 3rd group? We try and do that same plane. We don't have a plane of symmetry. The yellow can't reflect into the white. The same thing's happening with our halogen compound. The same kind of thing is happening with just butane. Where's the plane of symmetry within butane? I saw one hand showing that. So when I reflect across that plane, I have a carbon right there. Where is it? Going the other way. That'll be a fun one to try and draw. Like that. So I reflect across that, and that point is now here. It's the plane of the paper. There's your plane of symmetry. It's actually the board is where your plane of symmetry is. Right? It's where you actually wrote the structure. That's the plane of symmetry. Everybody saw that one right away. Yeah. Okay, this is why I find planes of symmetry very difficult to identify, which is why we go off of the easier aspect, identify an atom with 4 different things attached. So let's go through and take a look at the top one. This first carbon, does it have 4 different things attached? I only see one thing attached. It has 3 hydrogens. Is hydrogen different from hydrogen? No, so that doesn't count. Move to the next atom. So bromine is different from hydrogen. I'll give you that. Hydrogen is different from carbon. I'll give you that. But you're now going to tell me carbon is different from carbon? we have to continue to look through the rest of our structure. And as we look through the rest of the structure, the green hydrogen versus the red hydrogen, are they distinctive? And don't tell me they're different colors. Okay, they are different because the red hydrogen is connected to 3 hydrogens. The green hydrogen, or green carbon, is connected to 2 hydrogens, which means those carbons are different from each other, which then means 4 different things. That's a chiral atom. What happens if we look at the butane? How about at the end? I get 3 hydrogens. Can't tell a difference between them, so I can move to the next one. Oh, I've got an implied hydrogen. So is hydrogen different from carbon? Is that carbon different from the other carbon? Yeah. Are those hydrogens different from each other? No. So no chiral atom. So it can sometimes be easier to label or try and identify where the chiral atom is instead of looking for the plane of symmetry. Okay? It's kind of up to you to decide. Notice within the patterns, if you have a CH2, not a chiral atom. You have a CH3, not a chiral atom. When do you have a chiral atom? CH or C bound to anything other than hydrogen. Okay? Yes, we can draw on exceptions to that, of course. Okay? Do we now have a chiral atom in the bottom structure? Yeah, that should be a chiral atom. How about now? No. There's still no hydrogens attached, but we're now at least triggering for where we need to find that difference. Kind of make sense? Okay. So, all are our big definitions that come out of this. With one chiral atom, the relationship, or what we'll end up generating, is mirror images that are non-superimposable. If we define the relationship now between those 2 structures, they're referred to as enantiomers. So if I draw 2 random structures and say, what's their relationship? Okay, we said identical, different, constitutional isomers. Okay. Now, instead of it being stereoisomers, we'll end up throwing in enantiomers. Okay. So we've got to decide something about their superimposability. Okay. And that gets us enantiomers. But what happens if I have more than one chiral atom? I still have the option for enantiomers, but I also can generate a new set of structures that don't fit any other definition. Diastereomers come into play. Okay. The instant I bring in that second stereocenter, it also sets me up in a situation where I can draw 2 structures that appear to be different from each other, but are indeed identical. Because they have those chiral atoms, we won't call them identical anymore, we call them meso. Okay? The meso compounds, the big red flag is an internal mirror plane if you found chiral atoms. Okay? Now we got the definitions, you'll be experts at it, right? There's our flow chart now with everything on it. We still start with our same molecular formula, still look at superimposability, we'll still look at atom connectivity, but once we've established stereoisomers, we then need to look for chiral atoms. If we have a chiral atom, we move in to look at mirror images. If we don't have a chiral atom, that's where we hit our cis-trans systems. Okay? If we do have a chiral atom, then we need to look for mirror images. Okay? Is the relationship mirror images? If they are mirror images, they are defined as enantiomers. If they aren't mirror images, they're diastereomers. How do we get to the mesos? Mesos are a subcategory of the identical system. We're looking for those chiral atoms. Kind of make sense? Okay. So here's a structure. Draw all possible structures for this, or all possible representations for this individual compound. Okay. Which means consider where those chlorines are with respect to each other in space, but not connectivity. Part of it, yeah. So there's 4 structures drawn up here, and everybody goes, oh, well, I didn't draw 4. Okay, well, you may not have drawn 4. You should have drawn 3 to be perfectly correct. Okay? I would argue that you should draw 4 because you're trying to address all possible combinations. So in the world of all possible combinations, what you should do is very subtly change only one variable at a time. So I'm going to look at the top. I'm going to go across the top here and say the only thing I'm going to change is the black position. So instead of it being wedged, I'm going to make it dashed, which then means the other one must stay wedged. Because I'm only changing one thing at a time. To go down on the left-hand side, what's happening now? Well, I already changed the black position, so I'm going to maintain the black position and change the red position. Now when I go the other direction, what's going to happen? And I've now drawn all possible. So here's why we now want to evaluate, or why I want to see all 4. Are all of these unique stereoisomers? For them to be unique stereoisomers, they must not be identical to each other. Okay? And so by coming up with a kind of ordered method in how you go through and draw all the possible ones, you should be able to get all the possible and start to address where things are going sideways. So what is the relationship between the top 2 structures? And I would go back to the previous slide so we could see the little rules, but that deletes all my work, so I'm not doing that. Cis-trans officially really only works for double bonds. So we don't want to apply cis-trans to a ring. It is done occasionally, but it's not a good idea. Okay, those chlorines are different in space. If we take a look, the black chlorine is wedged coming at you in one case and dashed going away in the other. So they are organized different in space, which gets us into the stereoisomers, which is where you could come up with a cis-trans, but that's where we fall into a chiral atom. Do we have a chiral atom? Yes. In fact, we have 2 chiral atoms. So that's why we don't fit into the cis-trans system. The next question that we asked off of that slide was, are they mirror images of each other? Okay. This is the part that I hate when dealing with stereochemistry because I have to draw it all out. Okay, I would say, okay, I'm going to pick one to draw a mirror image of. And I now have my mirror image. Can I rotate this in any way, shape, or form to get that? No. So are they mirror images? No. Which then means the relationship is diastereomers. Okay. And I got yelled at on my evaluations for saying hate too much. So I don't hate it per se. I just find it very difficult because students can see it and I can't, and I have to draw it. And so it makes me feel like an idiot. What's that?
Is that what Ryder was here for right there?
Sort of, yeah. What's the relationship here? Diastereomers. How about here? And not to give away any subtle hints away. Diastereomers. And here? What is the relationship between these two? For them to be identical, they must be superimposable. Are they superimposable in their current state? No. If I took this structure and just tried to directly overlay it, the chlorines are aimed opposite directions. We could try and take the structure and flip it over. The instant I flip over this bottom structure, this dashed one will become out and at the other location. Okay? So they are non-superimposable. Well, but diastereomers are also non-superimposable. So what's the next one to figure out? Are they enantiomers? And so again, this is the frustrating one for me because what would I have to do? Draw out the thing. and then say, can I then superimpose that on the top structure? So I now know the blue one and this one are mirror images. Okay. So now what I want to do, and then on the diagonal between our upper two, we know those are non-superimposable. So right now I have two structures that are non-superimposable, and I have two structures that I know are mirror images. That's what I want to do. Take the blue structure and see, can I superimpose it on that structure? And if I just take this and flip it over, what happens? I get that one. So these are mirror images. These are non-superimposable. The blue in the top are, they're identical. Okay. These two were mirror images, or sorry, identical, which means these two being non-superimposable, these two mirror images means these two are non-superimposable mirror images, making them enantiomers. Suppose you're going, God, isn't that a lot? Yes, I agree. I think that is a lot of work. Okay? This is why I find it very frustrating when people can look at it and just say the answer. Okay, last one. What do you think? Enantiomers would be a good idea based off all the patterning here, except I did not show that as a blue arrow. What did I show that as? A green arrow, because they are not enantiomers. They are indeed mirror images, but they are superimposable mirror images. So they are identical, but I have at least two chiral atoms, which means meso, however you want to call it. If I'm now looking at my total stereoisomers, I cannot count one of those structures because it is already shown. And that compound in the upper left-hand corner is now known as a meso compound. How do I know it's meso? Look for two chiral atoms. Yes, it has it. Look for an internal mirror plane. That internal mirror plane and two chiral atoms is a big red flag for a meso compound. We don't have that in any of the other structures. If I try to draw a mirror plane in the upper right, it doesn't reflect across. One's wedged, one's dashed. Okay? Same deal for the bottom. Kind of makes sense? Okay. I'm going to erase it all. I'm going to give you a minute there to be like, that's what the question is. Okay, we'll get some pictures. I can accept pictures. That's fine. Okay. So when we do pictures, we should all do it at once, not this like, wait every 5 minutes to take a picture. Next person. Okay, next person go. You can all do it at once. So if we erase everything, total possible stereoisomer. Notice possible is in quotes. 2 to the n, where n is the number of stereocenters. So in this molecule, I had how many stereocenters? 2, which means the total possible stereoisomers I could get, 2 to the 2 would be 4. How many did we draw out initially? 4. Go figure. There it is. Okay. We will subtract 1 per any mirror plane within the structure. Why do we have to subtract 1? Because of the meso compounds. So what happens when we look at this guy? How many stereoisomers can we get for this? Okay, so as people are counting, let's try it this way. What are you counting? Stereocenters. Okay. So how many stereocenters are in the molecule? 2. Which was also not the question I asked. What was the question I asked?
What'd you ask?
Stereoisomers.
There's 4.
There's 4. I find 2 stereocenters. 2 to the 2 is 4. Is there an internal mirror plane?
No.
No. The structure, most structures you will find are so convoluted that it's either obvious that there's a mirror plane or it's not obvious. Okay? Where are those two stereocenters? Okay, we'll pick some place and start. Okay? Can oxygen at the very end be a stereocenter? Why could oxygen never be a stereocenter? I don't accept that. It can only have 2 bonds. We need 4. Nitrogen. Nitrogen can actually have 4 bonds if it becomes a cation, in which case it could become a stereocenter. Does it have 4 bonds? No. Carbon. Carbon could. Does it have 4 different things attached? No. It has a carbon, and a nitrogen. This carbon, it does have 4 bonds, but it's bonded to the same carbon twice. Okay? So any carbon that is sp2 hybridized is not an answer. So I can look at the sp3s now. I got 1, 2, 3, 4 sp3s. Can this one be a chiral atom?
No.
Why not? 2 chlorines. Can this one?
Yes. Yes.
2 hydrogens? No. Next one. Yes, what's the 4th bond? Hydrogen. And the next one? Yes, 4th bond, hydrogen. So we have 2 chiral atoms, 2 to the 2, 4. There's our answer.
Do we get to use our calculators on the next exam?
So, interesting question on using your calculators. Yes, but probably not for this reason. You can use calculators probably for the spectroscopy and calculating formulas. I'm fine with that, though you could probably do it longhand just as easily. I do not expect you to show work for this. So it would be 2 to the 4 or 2 to the 2. And I don't expect you to solve because I can figure that you can hit 2 power 2 and have the calculator spit out an answer. Yeah, the calculator will make you, or homework will make you do more work. Okay. You want to do some more relationships? Okay. So we've got the structural representations. Okay, so this is something that you've got to watch out for. Remember, we may have moved into looking at enantiomers, diastereomers, and all that kind of nasty chiral stuff. That doesn't mean you aren't responsible for all the other definitions that you already had. Okay? So in the lower right-hand corner, all that happened is we took the methyl group that was originally out as a substituent and moved that in directly attached to the ring. Okay, we've changed the numerical location of our methyl group. That's now a structural isomer. And as soon as we've identified that, that nails down 3. Half of our answers then immediately are pinned. Okay. What's the relationship between the top 2? Okay, that was fun. There's 3 common answers that we could use, and I got all 3, enantiomers, diastereomers, and meso. Okay, so 2 of you are wrong. For it to be meso, we have to have an internal mirror plane. There has to be a line of symmetry. There is no symmetry within that molecule. Okay, so no internal mirror plane, no meso compound. Now the question of diastereomer versus enantiomer. One of the things we could look for is, are there at least 2 stereocenters? Yeah, well, that didn't help us. Because if there was only 1, then it has to be an enantiomer. It can't be a diastereomer. For it to be a diastereomer, we must have 2. Okay? So we have at least 2. So we have at least 2. So that doesn't work. What happened to the OH, the top one? Okay, it switched. Okay, it effectively became its mirror image. So the top is a mirror. What happened to the bottom? Stayed the same. If only one position mirrors, it can't possibly be a mirror image. That would look like a really goofy hand. Okay? Which means, if it's not enantiomers, they're diastereomers. How about these 2? And I won't be nice. I'll just keep it as the same color. So again, we look at the top chiral position. What happened to it? The OH went from dash to wedged. Okay. We could say it mirrored through the plane of the structure. Okay. What happened to the other position? Went from wedge to dash, so it mirrored as well, which means two positions mirrored, enantiomers. And then our last one. Okay. We again switched only one, so we have diastereomers. Okay. How else could this question be made more difficult? Notice that the structure was drawn and directly copied across. All we did was exchange wedges and dashes. I could have just as easily, instead of drawing it directly across, picked it up, flipped it over, rotated it, and then drawn all my wedges and dashes. Okay? All of those permutations you're responsible for. Okay? This is, again, why I struggle with this section, because I have to draw out each and every single one of those permutations. For an individual problem, I have drawn out 5 structures. Okay? And yes, it sucked, but I got it right. Okay? Questions? Identify if the molecule is chiral or can be chiral by marking all stereocenters and determine the possible stereoisomers. So more practice. Take a look at the first one. I would say I sleep like a baby. And I know exactly how a baby sleeps, and not well. Leftmost structure. Do we have any chiral atoms? We have 1, which means possible stereoisomers. We get 2 possibilities. Next one. Why is there a wedge then? It's not so much that we want to mess with you. You will draw wedges and dashes randomly on your structure for no apparent reason. The reason we use wedges and dashes is to identify and kind of mark our chiral atoms. You're screwing with the system by drawing them on randomly. So we now have to counter your screwing with us by testing you on it. Okay? There is no chiral atom in that next structure. Okay? If we go out, we have chlorine as 1. We have a hydrogen as 2. We go out, we have a carbon as a potential 3. We go out the other direction, what do we encounter? The exact same type of carbon, another CH2. If we don't see a difference, what do we have to do? Move to the next atom. Move to the next atom, and what do we end up with? Same. And then what happens? They encounter each other. We found no difference, which then means there's only 3 things attached to that. Using the wedge was completely and utterly useless. Next structure. One, 2, and 3. Okay. So we do have 3 chiral atoms. Which one are you questioning?
Why was the top one?
We go out to a CH3. We go out to a CH2, and then out to a CH2, and that's where you're like, they're the same, right? What do we do when we see it, the same thing? Go to the next position. I have a CH versus a CH2. Is there a difference? Yes, it is a chiral atom. How far out do you have to go to find a difference? Until you find a difference, or you've reached the end of the structure.
So it doesn't matter, just those 2 connected to it.
So if we make a quick edit here. To identify if we have a chiral atom, we would have to track through there to see if there's a difference. Is that annoying and tedious? Yes, but that is theoretically what you would have to go through and do. Okay? Typically, the furthest you have to go out is 2, sometimes 3, because nobody wants to draw that and actually count it. Neither you nor the instructor had to draw it. Okay? But if you find a difference anywhere in that chain, that then says all the way back to the parent if you have a difference. Okay? So with 3 stereocenters on that one, we end up with 2 to the n, 2 to the 3, which gets us 8. Do we have any internal mirror planes potentially with that molecule? It's tricky to see, but no. There is no way that you could draw a mirror plane through that. So you end up with 8 possible stereoisomers. Not horrible? Maybe horrible. That's why we were supposed to talk about it last week, so you had some more time to practice on it. Physical observations. Okay. So this gets into kind of experimental aspects. Are there physical properties in a pair of diastereomers that are different or the same? Yes, good answer. That would be followed by what physical properties? Different ones. Well, they would be the same physical property. The properties themselves would be different from each other.
Arrangement in space.
Arrangement in space. Why would the arrangement in space matter? I'm recording, right? Yeah. There we go. We do a quiz on why. I'm just kidding. What keeps these 2 pieces of paper together?
Your fingers.
If we ignore my fingers, what's going to keep them together?
Friction.
The friction between the papers. Are the papers different?
Yes.
It's the same amount of paper, right? Now when they interact, what's going to keep them together?
Nothing.
Same or different from the previous situation? Different. What is it different about? Less surface area. Does the shape of the molecule affect a physical property that we have already discussed this semester? Yes. What physical property? Melting points. Okay. If we take a look at the left structure, we kind of have, yeah, I got it drawn there nicely. We've got the Hayworth projection shown for it. We've got the methyl down and a methyl up. Kind of zigzag, or zigzagged? Sure, zigzagged. What about the other structure? No, it's zigzagged. I don't know what you're talking about. What about the other structure? Which of those is going to stack nicer? Right. It's not the same. One has kind of like a back of methyl groups and then a seat. The other one has this weird kind of staggered thing going off of it. Okay. We're going to change how those molecules interact with like molecules, which then means their melting points will change. If we add in a solvent, because their shapes change, how they interact with other solvent molecules will change. The physical properties of diastereomers are different from each other. Well, who cares? Let's see, did I do this right? Almost. Before we get there on it, who cares? How could we identify which one you made? We just said it, actually. Melting point. We can run a melting point to identify that compound. Okay. What happens when we move to enantiomers? They have the same orientation, just opposite. Which means, how are they going to stack? Exactly the same for both molecules. Which means what happens to their melting points? They're the same. Their boiling points, they're the same. Why does that become a problem? To identify, that could be a problem. We don't know which one we have. One of these drugs cures cancer, the other one kills you. Let's identify them by a melting point. We get the exact same answer. Well, 50-50, let's just do it. Okay. Whoever dies, we'll stop using those. Okay? Generally not a good idea. Okay? So how do we come up with a method to identify it? Well, that's one of the problems with enantiomers. Enantiomers have similar properties. They're just kind of mirrored of each other, which means to separate them becomes virtually impossible. They have different melting points that are identical to each other, okay? But when we make them, they get mixed in, okay? Which makes them naturally impure. If we look at their structures, they look the same. How can we possibly separate these if they act the same with achiral substances? We take a look at problems. Naproxen. Okay? One is an anti-inflammatory. The other one destroys your liver. That may be worth it if I'm in enough pain. Okay? One, limonene. Smells like citrus. Cool. I can add R-limonene into a solution and makes my house smell beautiful. But the guy in the lab wasn't paying attention and added S-limonene. And now my house smells like turpentine. That's a pretty big difference. Okay? Carbone. One smells like mint, the other one smells like caraway. Why are we seeing different properties with how we interact with these molecules? We are chiral. The only way we can tell a difference between our enantiomers is to have them interact with a chiral molecule. Achiral molecules will exhibit no difference whatsoever. That's how we'll take advantage of trying to separate them. That's where we'll start.